Okay, next is exercise 44. In this one we are given a set z7 of root 3 or z7 root 3 whose elements look like this: a plus b root 3, where the elements a and b are coming from z7. We have to prove that this set is a field. And then there is another part to this exercise. The next one asks us to do this. For any positive integer k and any prime number p, of course also positive, we have to determine a necessary and sufficient condition that this be a field, just like this one. We can see that in this special case k is 3 and p is 7. So what we are going to do here is that we are going to handle the general case itself. That is, we are going to work with this. That means we have to show that under a given condition, which hence is going to be a sufficient condition, that this will be a field. And then we will show that if the condition is removed, then it does not become a field. That means the condition is necessary also. And then as a consequence of that, this will just simply come out, that this hence will also be a field, because whatever condition we are going to put forth, this will satisfy that condition. Okay, so let's start the solution. Let me just see one thing. Oh, I forgot to write this, although it's understood, but still here the elements look like this. Okay, this we want this to be a field. We have to find a necessary and sufficient condition for that. Okay, so let us start. For a plus b root k and c plus d root k in the given set, we define a plus b root k equal to c plus d root k if and only if a is equal to c and b is equal to d. But the question is, why do we need to define equality in this set? Do we not already know this? Actually, we do not know this. Why? Because you see that these symbols are not complex numbers. They are just some abstract symbols. And that's because parts of this symbol, that is this a and b, they are not real numbers. Also, they are not complex numbers. So although it looks like something familiar to us, say a complex number, it is not. It is just some abstract symbol. So we need to declare when two such symbols are equal, and we do so here. Okay, so now we are going to say that two such symbols are equal if and only if the corresponding components, I can say it like this also, you understand that by corresponding component I mean that, for example, this one which is not there with root k, that is one component, you can call it the first component, and the one that is with root k, that is the second component. So two such symbols are declared or defined to be equal if and only if their first components are the same and also the second components are the same. Okay. Also, now we are going to define addition and multiplication in this set. Since we are dealing with abstract symbols, so everything has to be defined, and then based on what we define, we are going to see the consequences, that is whether it will be a field or not. Also, so let us first define addition. A plus b root k plus c plus d root k is defined to be equal to, since we are defining, so we put a colon and then write the equality sign. Whatever appears on the side of the colon, that is the thing being defined, and its meaning lies on the other side. And you can guess what it's the most natural definition. You just add the first components and you also add the second components, follow that up with root k. But we also need to define multiplication. C plus d root k. So you just need to see what you will get if these were real numbers or say complex numbers, and you would normally multiply things out. So you want this to be SC plus KBD plus AD plus BC root k. Since we want this, we have defined it to be just this. So immediately we can see that our set is closed under this addition and multiplication, which actually means what? It means that this addition and multiplication as functions are well defined. You should always remember that these are also, being binary operations, they are functions. For example, the addition is a function from this Cartesian product into this set. Is this function really well defined? Let us see. Say you consider two such symbols, and the ordered pair that you would get out of them, whose first coordinate is this symbol and the second coordinate is this symbol, is an element in the domain of this function class. That is, it's an input for class. So for that, the output is this, which is unique, which is again a unique such symbol. And where is that uniqueness coming from? That uniqueness is coming from our definition of equality. Our definition of equality says that any such symbol has only one representation as such a symbol. That is, two such symbols having different first coordinates or different second coordinates or different both cannot be equal. So that's why for a given symbol like this, A and B are uniquely determined for that symbol. Just like that, for this symbol, C and D are uniquely determined. So A and C, B and D, these are unique elements in ZP. So their sum in ZP is also a unique element in ZP, just like that B plus D is also a unique element in ZP. So that is why this is a unique symbol again here. So each input has a unique output. So that is why this is a well-defined function or a well-defined binary operation. And when we casually say that our set is closed under the operation, all these things are there in the background. But you can clearly see that it's true. Okay, so plus is well defined, and in a similar manner, this is also well defined. The product is also well defined. Again, for given a plus b root k and c plus d root k in our set, the product has been defined like this. We understand what AC and BD are, but what about KBD? Because you see, B and D are not ordinary integers. B and D are elements in ZP. They are actually not ordinary integers, but in ZP, KBD means BD plus BD plus like that K times, and that after all is again a unique element in ZP. You add that up with AC, you again get a unique element in ZP. And here, however, you do not have that K problem. It is just simply AD and BC. So AD plus BC is a unique element in ZP. So this again is a unique symbol in this set. So just like addition, the product is also a well-defined binary operation. Fine. So let us now verify the first few axioms. Let us show that at least our set is an abelian group under the operation plus. Keep in mind that the necessary and sufficient condition that is being asked for in the exercise, we haven't said anything about that, but we will. Okay, so this part of course is not a part of the solution this much. Let a plus b root k, c plus d root k and e plus f root k belong to our set. Then just now I have just simply mentioned these things verbally, but we need to write. Then a plus b root k plus c plus d root k, which is equal to a plus c plus b plus d root k. Of course, it belongs to our set. Now this of course is a part of the solution. After defining the operations like this, we generally write some things like that. The question is, why do we normally not mention this uniqueness of output and the function being well defined? That's because in most of these cases where we define some operations, the operations are defined so naturally that the uniqueness is almost obvious. So we just make sure that the output belongs to the codomain or range, whatever you may want to call this second set in a function. Okay, so we just simply normally write this. So that means our set is closed under plus. So that is one thing. Then That means our sum or addition operation is commutative. And keep in mind, no matter how casually we are going on calculating like this, always make sure whatever you are writing is actually true or not. A and C are elements in ZP, and the plus that you see here is the plus in ZP, which we know is commutative. That's why A plus C is equal to C plus A, and that's why B plus D is D plus B. Next, we verify that addition is associative. Yeah, E plus F. A plus C plus E plus B plus D plus F root K. And in performing this sum, this is the operation, we are strictly using just the our definition of plus and nothing else. We cannot do anything else. That's because we are dealing with abstract symbols, so we don't really know what they are, what they represent, or how they behave. The only rules right now we have are the equality of two such symbols, the addition of two such symbols, and the multiplication of two such symbols. So so what I am trying to say here is that you cannot do your ordinary multiplication like what you ordinarily do with this kind of symbols as if these are real numbers and then take root k common out. No, we don't have those rules here. We are starting from scratch, so we have to stick to whatever rules we just have and then move forward. That's what we are doing. Now inside we can do whatever we want, because inside these square brackets our calculation is happening in ZP, and we know that here addition is associative. So here we can write A plus C plus E and B plus D plus F root K, and this equals, again by our addition definition, plus C plus E plus B plus F root K, and that in turn equals A plus B root K plus C plus D root K plus E plus F root K. So we have proved that addition is associative as well. Addition is well defined, addition is commutative, addition is associative. Next, let us put a full stop here, a period here, and then continue. We have zero plus zero k belonging to our set 0 plus 0 root k such that a plus b root k plus 0 plus 0 root k is equal to, let me finish writing this, then I want to say something about this element. This is nothing but again a plus b root k. Whenever we see something like this where everything is 0, every component of a symbol is 0, we are tempted to write just 0, but you cannot do that here. Why? Because in our set just 0 has no meaning. It has not been defined. What is 0? This set has only symbols which look like this, and among them this is one particular symbol where both the components are 0, the 0 element in ZP. If you want to call this element 0, you have to define that this will be called 0. Then only you can write this plus 0. And also keep in mind that we are again carefully applying only the definition of addition. We are not just simply saying that, oh, okay, so we have 0 here, so we are going to get this same thing back. No, you have to actually see whether that is true or not. Yes, it is true. And one more thing is that, so you can understand that this, I am going to call this now an additive identity or a 0 element. But for that, really we need to also show that this plus this is also equal to this. But in this case that need not be shown separately. Why? Because we have already shown previously that addition is commutative. So if this is this, then you switch the order, that sum will also be equal to this automatically due to commutativity. And you need not even mention that. Finally, minus a plus minus b root k belongs to our set of symbols such that, and you can guess or you already know that this is going to be an inverse of a plus b root k. And here also we need to be careful. At least if we should not be sloppy with these things, because that may make us mistakes, terrible mistakes, such that a plus b root k plus minus a plus minus b root k is equal to a plus minus a plus b plus minus b root k, and that is 0 plus 0 root k. Again, we are not writing 0 here simply. So what I wanted to say here is that, do you see that I have not just simply written minus a minus b root k? Why? What goes wrong if we write like this? Actually nothing goes wrong, but in the beginning itself, but still paradoxically something goes wrong. If you want to be somewhat sloppy and somewhat casual, you can write like this, which someone can make sense of this, but this set consists of symbols which look like this, and there is a plus which is a part of this abstract symbol. Do we have that plus here? No, we don't see that. And by the way, in this symbol, what is the first component and what is the second component? Are they A and B? No, you would say that they are minus A and minus B. But then you should actually have written this, not this. That is why. In a sense, this is equal to this, but that comes only after we couple this addition with multiplication. Okay, and then break down this symbol. Those things are there, you need not worry about that. Right now, let us just be rigorous and try to avoid making mistakes. Okay, so what are the things we have shown so far? Addition is well defined and the set is closed under addition. Addition is commutative, addition is associative. This is an additive identity and every element has an additive inverse. Hence, our set is an abelian group under the plus operation. Next, of course, the thing continues. Next, you have to handle multiplication, and in multiplication, what are the things you need to show? Again, the set is closed under multiplication, which actually really means that multiplication is well defined like addition, and as a result, the set is closed under multiplication. Multiplication is associative. Okay, and the two distributive laws are true. If you manage to show these things, that will turn your set of symbols into a ring. But we have been asked to prove even further than this. Namely, what are the extra things we need? Multiplication is not just associative but commutative, so it becomes a commutative ring. And there is a unit element. Unit element means there is a unity. In this book, I think we call the unit element unity. So the ring has a unity and it is commutative. And then comes the task of showing that every non-zero element has an inverse under multiplication. So the task of showing that, the remaining part, at least till you show that there is a unit element or a unity, that I leave to you. So I am leaving the messy part to you. Messy means computationally heavy part to you. So after this, show that, so you have to handle this part. The multiplication we defined above means towards the beginning of this solution is well defined and hence our set is closed under it. That's the first thing. Multiplication is associative is distributive over the addition we defined above and 1 plus 0 root k belonging to this is a unity. Once you manage to show these extra things, then your set has been turned into a commutative ring with unity. So suppose that you have shown these things. Now we impose that condition that we need in order to make this a field. Note that so far without any further restriction on p and k, say p is any prime and k is any positive integer, this will be a commutative ring with unity. So this part is left to you. Now we continue. Now suppose the equation x square is equal to k has no solution. In this field, we already know what the elements in this field are, all the non-negative integers less than p. We should not really think of them as integers because the addition and multiplication are not ordinary addition and multiplication of integers but modulo p. If you want, you can think of the elements in this as congruence classes modulo p. Whatever you your interpretation is actually does not matter. Okay. Now, given the positive integer k, it may or may not be the case that there is an element x in ZP such that x square is equal to k inside this system. Okay, it may or may not happen. Another way of saying the same thing is that square root of k may not exist in ZP. If it exists, then this has a solution, this equation, and that solution will be called square root of k. For example, in the system of real numbers, we have solutions to this equation. Two solutions are there and you already know that they are -1 and 1, whereas this equation has no solution in this system but has two distinct solutions in the system of complex numbers. Okay, so the situation is like that here. Instead of this real field or complex field, we have this finite field. In this finite field, say this equation has no solution, which just simply means that there is no element x in ZP whose square is equal to k. So this is our condition. Now we want to show that under this condition, this will then be a field. That means, provided we have shown that it's a commutative ring with unity. Now the extra thing we need to show, of course, is that every non-zero element here has a multiplicative inverse. So let us consider a non-zero element. Let x plus, we have taken x, it does not matter actually. This x is a variable, no, there it looks a little odd. This x is a variable, so let's take u plus I. See how familiar we get with this kind of things. I was going to write u plus iv, u plus v root k this such that it is non-zero, that is, this is not equal to this. Not equal to means what? U is not equal to 0 or V is not equal to 0 or both are not equal to 0. Okay. Suppose that the thing that we will have here is u square minus kb square. Okay. Suppose u square is equal to kb square. Suppose, okay, u square is equal to kb square. Keep in mind what is the meaning of this equation. U and V are coming from where? Coming from ZP. So they are actually not ordinary integers, but K is an ordinary positive integer. Kv square means V square plus V square plus V square K times. So that is the meaning. But whatever the situation is, after all, this equation is to be interpreted in this field ZP. Now if V is equal to 0, see, we need only U to either be non-zero or V to be non-zero. Maybe it's the case that V is 0 and U is non-zero, that is allowed. But if V is 0, then U square is equal to 0, since this is a field, we then have U also equal to 0. Why? That is because if U is non-zero but its square is 0, then by definition U becomes a zero divisor. But ZP is a field, it cannot, being a field, it's an integral domain, it cannot have a zero divisor. So that's why U also has to be 0. But then we have violated this condition, a contradiction. That means V cannot be 0. Not equal to 0, and this implies if V is non-zero, then we can divide on both sides of this equation by V square. If V is non-zero, V square is also non-zero because we are in a field again. And doing that in this field, you get this. Where U divided by V is obviously an element in ZP. Let's write that. but this is a direct violation to what we supposed there, what we assumed there, that equation x square equal to k has no solution in CP. But this contradicts our hypothesis. That you understand which one. And why is this contradiction arising? It is arising because of this supposition that this is equal to this. So our supposition is wrong, i.e. u square is not equal to kv square, or u square minus kv square is not equal to 0, and this non-zeroness of this element is of course in ZP. It's an element in ZP. That means it's a non-zero element in the field ZP. ZP is a field, so its own inverse actually exists in ZP under multiplication, the multiplication operation that we have in ZP. And due to that fact, now we will be able to write a symbol from our set, this set, that will be the multiplicative inverse of this, and that symbol is this. So u divided by u square minus kv square plus minus v divided by u square minus kv square root k belongs to our set of symbols. Let us again see carefully. This is non-zero. This is a non-zero element in this field, so its reciprocal or multiplicative inverse exists, and that is why we can consider it in the denominator, and which makes this and this elements in ZP, and that is why this entire abstract symbol is again a symbol in ZP root k. But let us now do the multiplication and see whether we are getting the unit element or the unity in our ring of symbols that we previously mentioned, and that unity is 1 plus 0 root k. So this such that because multiplication is commutative, you just need to see one of the two products, and by that I mean u plus v root k times this minus v divided by and keep in mind we are dealing with multiplication, so we have to use the definition of multiplication. This times this, first component times first component plus second component times second component, that gives us the first component of the product. U square, well, not just that, but we have to multiply a k here also. You go back to the definition, there you will see a k here. So u square divided by this plus k times v times minus v. This is one thing, and this times this plus this times this, and here we do not have any k. That means u times minus v plus this times this plus this times this, v times u okay. And you can now see that if you do this, if you do whatever needs to be done here inside the field ZP, because this calculation and this calculation are going to happen in ZP, then here you are going to get what? U square minus kv square divided by u square minus kv square 1, the one that you have in ZP, plus, and these two will cancel out, 0 root k. Yes, so you are actually getting the unity in your ring, and that is why this is a multiplicative, actually it's the multiplicative inverse of our non-zero element, and this proves that our system is a field. We can write here itself. So this is a field. Fine, but now let us lift the restriction. Let us get rid of the restriction that what was our condition, that x square is equal to k has no solution in our ZP. Now say it has a solution. Next, let x square be equal to k for some x belonging to ZP. Keep in mind that before that assumption or its negation, that is this one, we have already shown that, or rather you will complete the last part, that our system is a commutative ring with unity. That is true irrespective of these conditions. Okay, now we have this. Then x plus root k belongs to our set of symbols such that x plus root k is not equal to 0. Why is it non-zero? Do we know about x? We don't really know what x is. That will entirely depend on k and p. X may itself be 0 if k is 0, for example. Well, k cannot be 0. Actually, it's given that k is a positive integer. Still, we need not bother about x. This component, which is 1, oh, actually I should have written 1. Na? This 1 is not equal to 0 in ZP, so that is why this symbol is different from the 0 element in our ring. And what do we get if we square it? If you want, you can use the binomial theorem, which is still true in a commutative ring, but I prefer to again use the definition of multiplication like it is given. X square what the hell am I doing? See, I forgot what I needed to do. I started squaring it. x plus 1 root k times x plus minus 1 root k. Yeah, now I need to calculate this product. So first component times first component x square plus second component times second component, that is minus 1 okay. Shall I get what I am trying to get, or will it wait? No, I think this is not what I wanted to get. What was the element? X square minus k square. No? Here we are having x square minus 1. Okay. No, see, again I made a mistake. That's not the definition of multiplication, right? The definition is x square plus k times 1 times minus 1. Yes, I forgot that k. So even a slight mistake will make everything wrong. Next, x times minus 1 plus 1 times x root k. So that means I am getting x square minus k plus, already this is giving me 0, and now x square minus k is also 0. Now just like this is non-zero, this is also non-zero, because here we have minus 1. Just like 1 is non-zero, minus 1 also cannot be 0 in ZP, no matter what the prime p is, but their product is 0. So this is a 0 divisor. So we can write that since x plus minus 1 root k is not equal to the 0 element in the ring, so our x plus 1 root k is a 0 divisor. That means our ring is not an integral domain, and as a result it cannot be a field. So this is not an integral domain, and hence is not a field. So what is it that we have proved? We have proved that if the condition whose presence makes our set a field is lifted, then it is not a field. In other words, if you take the contrapositive of this statement, what we have proved just now, that if this is a field, then this should not be true. In other words, our original assumption should be true, that this equation has no solution. So that is the necessary and sufficient condition, one necessary and sufficient condition to make this a field. Now we go to that Z7 root 3 case. Note that the equation x square equal to k, no? So that means 3 has no solution in C7, hence this is a field. Actually, in order to solve this, we need not do all these things if we have the tools that is needed. The tools of field extension, homomorphisms, ideals, those things, but they are coming. We are yet to get those things, so they will come in the subsequent chapters. Because we have done so much, why keep this hanging? Let us see that this actually has no solution. So what are the things we have in C7? These 7 symbols. 0 square is of course 0, 1 square is 1, 2 square is 4, 3 square is 9, but modulo 7, 9 is 2. You divide 9 by 7, the remainder is your answer. 4 square is 16, again 2, because 14 is divisible by 7. 5 square is 25. 3 times 7 is 21, that means 4. And 6 square is 36. In C7, 36 equals what? 7 times 5 is 35 plus 1. So you do not see any 3 here. That's why no square in Z7 is equal to 3. In that way, it has no solution. Or in other words, in Z7 there is no root 3. That's the thing. Okay. Now there are of course the other exercises that we have after this, but let's just end it here itself today, because it has been really very long. Although I have in fact left the significant portion of the calculation part to use, still it has become long. So that's just it for tonight, and tomorrow we are as usual going to study analysis, where we are going through sums over infinite sets. I think we have just stated Fubini's theorem, so tomorrow we will start proving it. Its proof is fairly complicated, so we have to do it in chunks. It cannot be done in one video. Okay, so we will break it up and do the chunks separately. So with that, I just wrap things up. So see you tomorrow with Fubini's theorem, its proof. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.